Today, we're cracking open one of the most chaotic puzzles in the modern world: logistics. We're going to explore how a completely new generation of AI is starting to find order in all that chaos, solving problems that have frankly stumped computers for decades. So let's start with a question. Imagine you're in charge of a fleet of delivery trucks. How would you plan the most efficient route for every single one of them? I mean, it sounds pretty straightforward, right? But the real world? Well, it's anything but simple. And this really gets right to the heart of the problem. You've got this massive gap between the clean, simple map and our messy reality. On paper, everything's predictable. But out there, you've got traffic jams, sudden changes in what customers need, and of course, bad weather. Suddenly, that perfect plan of yours, it just falls apart. Okay, let's dive into this puzzle. Now, in the world of computer science and optimization, this challenge has a formal name. It's called the Vehicle Routing Problem, or VRP for short. So the VRP isn't just about figuring out a route for one truck. It's about finding the absolute best routes for an entire fleet, all while juggling things like how much each truck can hold and what each customer actually needs. This is what's known as a combinatorial problem, which is a fancy way of saying that with every new stop you add, the number of possible routes just explodes. I mean, for just 60 customers, the number of options is, well, it's a number so big you can barely wrap your head around it, making it an incredibly hard task for even the most powerful computers. This quote from researcher Martin Takach really nails the first layer of real-world chaos. Travel time isn't some fixed number you can look up in a table. It's totally random. One accident, one sudden traffic jam, and everything you planned is thrown completely off. Your perfect route can disintegrate in just a few minutes. And then there's the second layer of chaos: demand. You might think you know exactly how much a customer is going to need, but that can change in a heartbeat. The ice cream shop analogy is perfect. Things you can't control, like the weather, can totally change demand. So your routing plan has to deal with random travel times and random customer needs at the same time. So, for years, how have we tried to solve this incredibly complex problem? Well, let's take a look at the old school approach, and you'll see pretty quickly why it so often fails. So, the traditional method tried to tame all this randomness with statistics. The idea was, look at a bunch of past data, build a model to guess what the future might look like, and then generate a handful of these possible scenarios. Then you feed those scenarios into a powerful solver to find one route that works pretty well on average. It sounds logical, right? But it's got some really deep, fundamental flaws. The biggest flaw is that this whole method is just brittle. It assumes random events are independent, which is almost never true in the real world. A single snowstorm doesn't slow down just one truck. It snarls traffic across an entire region. Everything is connected. On top of that, the complexity just explodes. Trying to solve for just 5 possible future scenarios with only 20 customers is already pushing computers to their absolute limits. It's just not practical for the real world. So to crack this code, we need something way smarter, something that doesn't just calculate, but actually learns from experience. We need an approach that can adapt on the fly. And this is where a really powerful AI paradigm called reinforcement learning comes into play. The best way to understand reinforcement learning is to imagine a child learning a new task. At first, it's just random trial and error, right? They're just pushing buttons. Some actions lead to bad outcomes, let's call those punishments, and some lead to good outcomes, or rewards. Over time, after millions and millions of tries, that child, or in our case, the AI, starts to figure out a strategy to get the most rewards. This simple loop is basically the engine of AI learning. The agent, that's our AI, looks at its current situation, or state, it takes an action, and then it gets feedback, a reward or a punishment. It uses that feedback to update its internal strategy, which is called a policy. And it just repeats this loop over and over and over. And each time, that policy gets a little bit better at making decisions. Okay, so let's see how this learning agent is actually trained to become a master logistics planner, one that's capable of navigating our crazy, chaotic world. This approach has evolved a ton. Early attempts back around 2014 used models that treated the list of customers like words in a sentence. Now, that was a huge flaw because, unlike a sentence, the order of your customers shouldn't matter. It's the same problem no matter how you list them. The real breakthrough came with newer AI architectures, especially transformers, which actually understand that the customers are an unordered set. That lets the AI grasp the true nature of the problem. And the results? They really speak for themselves. This chart shows performance on what are called stochastic problems. That's our messy, unpredictable, real-world stuff. The bars represent the total cost of the routes, so a lower bar is better. And as you can see, the reinforcement learning agent consistently finds solutions that are 2 to 3% more efficient. Now, that might not sound like a lot, but in logistics, that adds up to absolutely massive savings. The AI's power gets even clearer here. When it was put head-to-head against established software, like Google's powerful OR tools, the trained agent found a better solution 60% of the time. This isn't just some theoretical improvement in a lab, it's a practical winner out in the wild. But here, this is the real game changer: speed. Once it's trained, the AI can find a new solution, a process called inference, almost instantly. We're talking milliseconds. This incredible speed means a dispatcher can reroute their entire fleet in real time, the very moment a snowstorm hits or a big accident happens. That is how you truly conquer chaos. So all this incredible progress leads to the question that's probably on your mind right now in the age of AI. If we have models as powerful as ChatGPT, can't we just, ask them to solve this for us? It's a really tempting idea, isn't it? But the answer, for now at least, is a firm no. Large language models, for all their amazing power, just aren't built for this kind of precise mathematical reasoning. They don't have the right architecture to solve these complex optimization problems directly. They are masters of language, not logistics. But hold on, the story doesn't end there. Researchers have found a brilliant new way to use these LLMs. Instead of asking for the final answer, they ask the LLM to act as a strategist. The model first breaks the big problem down into smaller chunks. Then it suggests a classic algorithm to solve it. Then it actually guides itself step by step through executing that algorithm. And finally, it pulls the pieces together into a complete solution. It's not solving the problem, it's reasoning its way through a solution strategy. Pretty clever. So the key takeaway here is this: we are teaching AI not just to compute answers, but to learn, to strategize, and to adapt in these deeply uncertain environments. The same principles that are being used to optimize delivery routes could one day manage our power grids, design complex new molecules, or untangle financial markets. The chaos code is being cracked. And that opens up a whole universe of new possibilities.